Okay, hello everyone. I just want to share you the QR code for Slido. So if you have any questions, feel free to type that in, and yeah, I will answer that directly after my talk. And the topic of my talk is scalable Java apps and microservices with EclipseStore. Short about me, my name is Kuemmel. I'm software developer and project manager for 15 years now. I'm part of MicroStream since 2019. Currently, I'm the project manager of the EclipseStore Cluster development, and I'm also involved in some Allianz and Fraport projects with cluster, without cluster, and yeah, that's it basically. The topics I want to talk, I will give you a really short summarization of EclipseStore, just for you to let you know what it is and what do we talk about. And then I switch totally to the journey through the creation of the MicroStream cluster. That means we decided 1.5 years ago to create a cluster based on EclipseStore. And we have to talk about various terms and their meanings, the architecture of the cluster, ideas, and the decisions that we made at the end. After that, we have a short look to a live demo. That means we create a cluster from scratch, or we create a cluster project from scratch. We deployed it to a cluster, and I will give you a short introduction into the cluster front end, how to deal with it, and so on. And last but not least, there is a roadmap I want to share with you. Yeah, I would say let's jump in. Okay, what is EclipseStore? EclipseStore, let's call it a Java native micro persistent layer. A lot of words, but it's Java native. It's small, that means micro, and it's a persistent layer. That means it takes your data and stores it somewhere. So, and it is a persistent, strong, consistent storage. And it's part of your Java application. That means for each storage, or each JVM has its own storage. It's a framework. On top of that, it took your object graph, and of course also the values, and it serialized it to a binary format. And this binary could be stored on any binary storage, I would say. It could be a persistent volume hard disk, it could be an S3 bucket, for example. And it could also be your relational database, as long as the database supports binary, but that should be the case all the time. And when you change something within your object graph, it persists the changes directly to the binary, and it updates the binary partially. I think that's an important thing, and yeah, that works great so far. At the end, EclipseStore is an in-memory database. That means by default, most of the data stays in memory. But there are some possibilities to set some lazy spots within your object graph, and all the data below that lazy spots stays on the hard disk as long as you stream through it. So when you call the get method on that data, it will automatically load from the persistence and will be merged or attached to your object graph within the RAM. And this is how it basically works. It's a framework. That's great. All the people that hear that on the booth, they told me, oh, that sounds great, but what about scaling? I mean, it's a framework, how to scale that, and there is only one JVM, how to do that. And that was the reason why we started 1.5 years to create a cluster. And this is the journey I want to share with you. First, when we start to evaluate cluster technologies and so on, there are a lot of terms and words, and you have to evaluate all of that. So there are types of scaling, different states, type of consistency, replication, and so on. But in my opinion, the three most important things are: we have to clarify what means horizontal versus vertical. That's important. And we have to make a decision what type of scaling do we really need. Most of you might say, okay, horizontal versus vertical scaling, that's easy. Horizontal means we add some new hardware units, and vertical means we raise CPU and RAM. But that is only the half of the truth. I come to that a little bit later. So, but as I said, vertical scaling, increase CPU and RAM. The pros are that's an easy scaling, no big issues. It's definitely cheaper at the end. And AWS, for example, guarantees you 99.99% availability anyway. So what could go wrong, you might say? On the con side, we have technical limitations. And one of that limitation, of course, is we are not able to scale limitless. Even if AWS now, I looked at their homepage, they enabled now an EC2 instance with 448 cores and 12 terabytes of RAM machines. So that's I'm pretty sure that should be enough for most of the projects. Yeah, that's quite big, but it's a limit. So anyway, but more important point is the high availability, and that means if the EC2 goes down, your application is no longer available. And that is different to the horizontal scaling. And it means an increasing number of hardware units within a specific structure. And that structure could be Kubernetes or, yeah, and some other alternatives to Kubernetes. Docker itself is not able to do that, but we talk about that later. So the pros at horizontal scaling are no limitation, not a surprise, and also the high availability is solved. On the con side, we have costly infrastructure and stuff costs, and of course it's highly complex, especially when we talk about stateful clustering. Next important point is scaling for what reason. Yeah, people always ask, does it scale? And I have to ask, scale for what? Scaling data, scaling availability. What do we have to scale? On the first part, we could talk about data scaling, and most of the time we talk about sharding. That means whenever you need a continuous increasing amount, or when you have a continuously increasing amount of data, then you will need sharding. That means distributing data across several smaller databases. So let's imagine we have 3 pods, like in that example here on the right, 3 pods, and each pod consists of different or a specific range of indexes. So it means pod 1 is responsible for the index 1 to 4, pod 2 for the index 5 to 8, and so on. So, and that could also be different of different types. So that it could be the case that pod 1 and 2 are responsible for customers, pod 3 for companies, pod 4 for orders, for example. So this is also a type of sharding. So and there is another possibility. It's the high availability scaling or fail-safe scaling. We mostly talk about replication because that is mostly a part of, there is data involved and so on. So, and that keeps the impact if something goes wrong as small as possible if something fails. Or keep the response time within acceptable limits, whatever happens to the system. And this is what I said, increasing or an abnormal amount of concurrent accesses that could happen, or something could fail. And at the end, it looks like this. We have 3 pods in that specific case, and all of the pods are carrying about the same data. And there is one load balancer at the beginning, and he routes the traffic to the pod which is not that busy, for example. Okay, stateful versus stateless. That's also quite important to know the differences. And there is one famous sentence, I would say, that says, if the server is able to store informations, no matter how big the informations are or how much informations, then we call it a stateful server. Or some servers or some resources are forced by their infrastructure to being stateful too. That means, let's imagine a server comes up and loads data from a database, and another server comes up 20 minutes later and it loads also the data from the database. Both servers doesn't have the same data at this time, and that's a problem. When you replicate stateful things, every server has to be the or has to have the same data. So, and that's exactly the point when we talk about stateless. That's an easy node replication. There is no data involved because it only replicates, yeah, services, I would say. So whenever, let's imagine we have create a report task, and in my opinion, it's sometimes quite heavyweight because the server has to collect data from the database and has to create PDF reports and so on. And this is a heavyweight task, and you could do this the easy way, create, let's call it microservice, put it on a Lambda, and when you need that report, the original server calls the Lambda, it wakes up, it creates the report, and it dies at the end. So that's easy scaling, stateless one. Each server does not need specific data at the end. And stateful, we talk about stateful things when we have to replicate data. And this is, here we are. So we have to replicate the data here, and this is highly complex at the end, and yeah, the biggest problem when we talk about scaling. Okay, but now we knew, okay, we need replication, we knew we are stateful because we are a database, and we decided to replicate. So, and then there are some more decisions to make, and we have to decide what type of replication do we need really. So there is one which is called async replication, and it works like, yeah, the request is incoming here. This is step one, and instantly you will get a response. So in between, the data will be stored on the writer node, and the replication happens in the background. So this is async. That means the write goes first to the writer, you will get the response, and the replication works in the background. This is, by the way, the most common use case when we talk about replication. And there is a second one, which is the synchronous one. And sometimes it looks a little bit different to that image, but the request is incoming here, and at the same time, all of the reader nodes gets the data at the same time, so the replication goes on. And after the data is fully replicated to all the reader nodes within the cluster, you will get the response back. There are many advantages and disadvantages on both sides, but as I said, the asynchronous version is the most common one because it's the easiest one and is the only one which works great on most of the cluster solutions. So the next thing we have to look is what architecture do we want to have? There is a single leader, multi-leader, or no leader. Let's start with the single leader. What does that mean? A single leader looks like this. We have one writer node and multiple reader nodes. And every traffic is managed, or specific the writer traffic, I would say, goes directly to the writer, and he manages everything to replicate to the readers. Most common replication is that because of the simplicity. Works great, and is the best combination of performance and strong consistency, or no stale data at the end. And especially for this, there is no specific use case. When we talk about different leader architecture, mostly it's because of a specific use case, especially the multi-leader. And multi-leader could look like this or look like this. And the point is the following. On the left side, we see this is an example of, let's say, data center replication. So we have one data center in US and one in Europe, for example, and we have to replicate the data between the two data centers. Then we have those cross data center requests made by the leader nodes, and this is, as I said, region replication or data center replication. And we have a second variation of that. It might look like the same, but it's different because when the request comes, we write it to the cluster maybe in Europe, And this task happens every 5 minutes, every 10 minutes, every hour, and it replicates the data to the second data center. And that's the difference between these two solutions. Here is the replication directly, and here is it after an hour, after 5 minutes, whatever. And the interesting thing is that there are not that much cluster on the market which deals with a multi-leader. Mostly you see multi-leader infrastructure when we talk about some offline modes and so on. Just remember when you use Google Maps and you load an offline map from Google, this is kind of like a multi-leader cluster, because every offline content on your smartphone is part of that big worldwide cluster, and it's handled via multi-leader. Or editing documents at the same time. For example, with, what is the name? Doesn't matter. Whenever you edit a Word document with two concurrent users at the same time, we're talking about multi-leader at this point. This solution is always eventual consistency. It could be made to strong consistence, but then the advantage of the better performance of multi-leader is gone at the end, and that makes no sense. The only thing which is important here is the performance is a little bit better than in normal situations, but when you force the cluster to be strong consistent, you will lose that advantage, and that doesn't make sense. And on top of that, there is a high risk of inconsistency with multi-leader. Okay, that's it so far to the leader or to the architecture. There is another multi-leader. I don't want to dive too deep into that. There is, as far as I know, there's only one technology I know on the market. It's Dynatrace and not Dynatrace. Sorry, DynamoDB from AWS. It's a no-leader clustering, and maybe there are some more, but I don't know that at the moment. Okay, last point at this section: what strategy do I need? Do I need a strong consistency? That means high latency but no stale data, or are we eventually consistent? I think every one of you knows that strategies. Okay, so that means we had to make decisions based on that, and that's not everything. So we didn't talk about infrastructure, backups, monitoring, logging, security, and so on. There is a lot of things to do within a cluster. So we made the decision. We want to have an asynchronous replication on our cluster with a single leader with an eventual consistency at the end. And that brings us the following advantages. We have a failover, a high availability, no data loss at the end, and no data inconsistency. That was the target of our cluster. Let's move on. Infrastructure, architecture, and deployment. Do you remember we are still a framework? We are no server at the moment, so then that could be interesting. When we talk about infrastructure and we talk about scaling and clustering, we have to make a decision which type of technology do we use as an underlying structure. We could use Docker like this. So we order a big EC2 instance, install Docker on it, and then we have the possibility to create containers and load balancers and so on. This is a great cluster, isn't it? So it will work. But at the end, it's not a horizontal scaling because it's only one machine, and you will not be able to add a second one and another one and so on. That means you created a cluster, of course, but this is not a real horizontal scaling cluster. And because of that, we are forced to move Kubernetes, because Kubernetes is the only platform which is able to bind multiple UI units to one pool of CPU and RAM. And that's you could see that here. You have to add or book EC2 instances to that Kubernetes cluster, and Kubernetes on top handles all the relations between. And then we have that load balancers, and we use container also like here. But the main, the main benefit of Kubernetes is we are able to handle multiple hardware nodes. Okay, but on top of that, we have to make some more decisions, because when we create a cluster as a service for you, then we have to make decisions to what kind of Kubernetes solution we use on AWS. Do we create an EKS, for example? Do we use Fargate or whatever? So yeah, let's talk about that a little bit later. Architecture, that is quite clear. So we have a lot of clients on the other side, and we have some nodes or pods here. So you see the writer node. This is the single leader I've told you, and we have 2 readers as an example. And in between the clients and those pods or nodes, we have one or multiple load balancers. It depends a little bit on the amount of traffic. The load balancers are mostly based on Nginx, and they scale dynamically up and down. It's an automatic solution built in Kubernetes. And at the end, we, in addition, need some backup functionality, of course, and we need an event streaming replication platform. In our specific case, we used Kafka at the beginning to replicate the data to all the reader nodes and so on. And this is what it looks like if we talk about a read request. So a read request goes to all of the nodes or to one specific node. This node returns the information and gives it back to the client. And a writer looks... Yes? We don't need to have to read. I think that's a misunderstanding. So the point is that we could serve read requests from every node. I think that's the point. Not all of at a time. Yes, that's right. Okay, and the write request looks like this. So it goes to the reader to the writer node and straight to the backup, and then from there it goes to the reader node. It will be replicated there. Now comes the question how to set up a cluster, and this was quite challenging because we thought about, okay, we just a framework, so we had to build a server on top of that framework and to create reader and writer nodes, right? So, and based on that, we decided at the first step, we decided to use Terraform as infrastructure as code platform to create the EKS instances and the EKS configuration on AWS. So that means when you click on within our front end, when you click on create a platform, then Terraform starts to run and creates the EKS platform for you. And if the Kubernetes is available, then we do the rest with Helm charts to create and configure your clusters. On the next step, we had to think about how to configure that cluster and how to configure the nodes that are on the pods and what software runs on the node within the cluster. And as I said, this was quite challenging, but we looked at a relational database and we see, okay, what do you have to do when you install a relational database? You have to install the database itself, or you have to use one as a service. You have to create tables and constraints, and you have to create a JDBC connection, define queries in your application, and call the queries, right? That's the way to use. On the other hand, when we talk about an example of Micronaut EclipseStore as a data provider, so that means we create a Micronaut project, like in the first point here, set up Micronaut, Helidon or Spring project, create a data structure. We create a Java data structure in it, so we create domain classes, customers, and so on. Then we create REST interfaces, and at the end we request those interfaces. That's the way it works. And that was the idea. So just set up any Micronaut project, Helidon or Spring, create your own REST interfaces in it or your own data structure, and at the end your REST interfaces, and then deploy it to that cluster. And we take care about to replicate the data in the background. And this works really great because we use technologies, they are quite standardized. So we used Spring and Micronaut and so on, a well standardized frameworks. Then we have EclipseStore in the middle, MicroStream as the cluster API, and REST, and that's it. And that brings me to the point that our cluster is a central point for hosting your application. And at the time, we will provide different types of clusters and solutions based on your application. That means you create your applications on your local device, and then you hand over it like on AWS Lambda, and we do the clustering in the background for you. And we try to hide you as good as we can from all the security stuff, HELM, Kubernetes, infrastructure, and so on. And it's, at the end, a fully managed Kubernetes configuration. And now it's time for a demo. So let's jump in directly. Let me just share. Okay, so I need to know where I am. So, okay, let's start here. So this is, I think this is what you see when you first time visit our cluster, our UI frontend, or our cloud solution, and you will find a starter project, or you can download here a starter template for a specific type of for a specific type of technology. That means you see you could choose here Micronaut or Helidon or Spring. For the moment, Helidon, we worked on it because we have to rework the integration, but Micronaut and Spring Boot is available. You choose the version of the framework, you choose the Java version, and then you could add your own package and the name of your project. And then you click on Create, you will get a download, and this is the template you could use within your IDE. There are some videos and introductions here that helps you to start. At the end, you see there is a project like this. I created this a long time ago. It's a cluster demo, and we jump directly into the code. Could you read that? It's not that important to understand what happens here. It's a normal, really straightforward Micronaut project. This is the POM XML. We see that there is the MicroStream Enterprise Cluster Node library is in it. That's important. We need that for the replication part. Then let's jump to the application YAML file. This is the configuration of the Micronaut and EclipseStore configuration within Micronaut. Then we need one data root class. This is maybe that's interesting for you. For EclipseStore, you always need one root object on top of the graph as an entrance point for EclipseStore itself to store those things. And within that root, I have one list of products, one get method. That's all. Then we need the product object itself. It's a really straightforward domain object, nothing special in it, some get and set methods. Yeah, nothing special, as I said. And after that, you create your own get, put, post interfaces as usual. As I said, this is nothing special, really straightforward, and that's it. So we will be able to click on start, and we could test this locally, no problem. Now it's done. So we finished the development. What next? So we jump back to the cloud frontend. Let's have to find it. Here we are. Okay. Now we are here. So the first step you have to do is we have to create a platform. And this is what I told you at the beginning. We decided to create an EKS cluster or an AWS account for each customer. The reason for that is most of the customer want to have a private internet connection or a private network connection to an account. So, or some of you might already have an AWS account, and you don't want that the data touches the open internet. So, and therefore we decided to create your own AWS account on our site. And this enables us to create a private connection. That means the data goes directly from your data center to our data center. And that makes things much more secure at the end. So that means you create a platform. This platform is, at the moment, AWS is the default ones, but we are working on Google and also on Azure. You choose the region of your platform. And at the end, so for example, you could choose Europe, and I have to add a name, doesn't matter, and now you could create a platform. This will take around, half an hour, because we have to set up a lot of things in the background. We have to do a lot of configuration on the platform. And that's why I created one this morning. Okay. Next step is, let's deploy a cluster to that. So we click on Add Cluster. And now that gives you the possibility to choose the basic pod size you need. So there are different strategies. So the first one, you have to decide which cluster base tier. And the base tier, you have to imagine some of you might have a lot of data, a lot of requests. And it makes sense to have a lightweight infrastructure in the background of the cluster, but some of you might more heavyweight things within your cluster, more load balancers, a much stronger Kafka for replicate the data. Then you have to choose a medium-sized cluster base because of the different prices. And you see that here, the minimum node count is 1, but you see the maximum node count 2, 5, or 10 nodes. And you also see the maximum storage sizes you could have within one cluster tier. So let's choose the smallest one. And you see here down there the different node sizes which are enabled in that cluster tier. So we have 500 millicores, 1000, and then the different RAM sizes at the end. You might say, okay, that looks really suspicious, but you will see that EclipseStore doesn't need that much CPU because it's an in-memory solution. We don't need that much CPU, but we need RAM because we are an in-memory database. And that's why we have low CPUs but higher RAM sizes. Okay, and then you make the decision how many nodes do you want. And the maximum node size is 2 in that cluster tier, which is the small one. The maximum amount of pods we have is 2. Okay, after that, let's click on Next. So we could add a name for the cluster. We have to choose what type of framework we use, Micronaut or Spring. Let's choose Micronaut. And then we could add our link to the repository. Say, okay, let's add it here. And we have to choose the branch, which is the branch that contains the current project, and say Next. Now we could configure the backup strategy. How many backups do we need? Do we want to have 2 times a day, once a month, and so on? Then we have to choose a cluster authentication, which is the basic authentication is available for the moment, but we are working on it to add some further authorizations. And there is, as I explained you, the AWS private link to the EKS. So that means that the data doesn't touches or do not touch the internet. So you can configure this. And on the other side, in your company, your guys from the IT know what to do when they see, okay, private link. That's great. So let's choose Next. Now we have some proxy settings. And this is also an interesting point. The question was always how to ensure that a write goes directly to the writer node, or a post goes to the writer, and a get gets to the reader nodes. And this could be made by the normal HTTP methods. So that means put, post, delete, and patch goes to the writer, all the others to the reader. But it could also be routing via an URL path. So you could create a specific URL path and everything within that path goes to the writer. And there is another possibility. You could add some header values to identify reads or to separate reads from writes. So I would recommend to use the normal HTTP methods. Let's click on next. And then you have the possibility to upload an already existing storage. That is might be also helpful. Maybe you already have a storage because you run your application in production before, and then now you move to our cluster, and then that enables you to create an already existing, or you could add an already existing storage. So click on next. Let me just double check here. I missed something. So, oh, come on. Oh, great internet connection. What happened? Okay. So it should look like this. So this is an already running cluster at the moment. I started it also this morning. And you see it's the same configuration like we do now. We have 2 nodes in it. And let's double check. So let's copy the URL. There is no data in it, but just to call it, it's enough to see, okay, there is an empty result of products within. So the access is working and in this case. And there are some details which are quite interesting. So when we click at details, you can see all the metrics on top. So how is the CPU consumption of some nodes? We see the 2 nodes, the main nodes, I would say. Node 0 is the writer node and node 1 is the reader node. At the moment, there is no traffic on that nodes. You see some additional nodes. This is a writer proxy and a normal proxy we use. In some cases, that might be interesting that you can see what is the so I guess the proxy on the right is the load balancer. And then you could configure your cluster here at the end. So you have possibilities to change the Git directory and to change the framework and so on. In addition, we have some further backup configurations. You could change the backup interval and you could create your own backup now. So for example, if you want to have now a backup of the data, you could download it. We have some monitorings here. That means let me just add some more information so we will see the metrics of the systems. So it needs a little bit. Let's just wait. So you see how much millicores are used at the moment. I think that's really helpful to see that at the end, and especially in production. And it's the same on the logging side. So when we call the logs, then you will see all the logs from the different servers within the cluster. And that helps you to get all the information you need to check if everything is working great and so on. Okay, some small steps, or at the end, some smaller informations regarding the profile. So here you can see your billing tabs, your oh, come on. Oh, something went wrong here. Okay, here. Internet, do your thing. Okay. Yeah. Not that important. Let's switch back to the presentation. Okay, last but not least, I want to talk about the roadmap of the cluster or the features we currently have. So as I said, The available cloud platform is AWS at the moment, and we are working on Google Cloud and Azure. Supported frameworks, I already told you that, Spring, Micronaut, Helidon. We support a JIT and jar deployment for the moment, and we are also working on a CI/CD deployment via REST, so that enables you to create your own cluster from remote. And we provide individual tier sizes, CPU, RAM, memory, and individual numbers of replicas. That is what we provide for now. Basic authentication, private connection support, individual backup strategies, routing strategies we talked about, monitoring, logging, and so on. And more important, this is the roadmap. So as I said, we try to, we're working on Azure and cloud. The supported deployments, we talked, CI/CD Jenkins possibility. We worked on an auto-scaling feature. That means you could say, okay, I want to have maximum 2 and minimum 2 and maximum 5 servers. And if the traffic goes down, the server will be shut down at the end, so that you save money and costs at the end. And we are working on a bigger cluster type, especially for big data clusters, for scaling data at the end. This is what we're working at the moment. Okay, now it's your time. So let me just switch to Slido. Hopefully there are some questions from you. First question, how can I set up it locally? That's a good question. Thank you for asking that. This is we talked about the service, right? So this is a cloud platform, it's a service and you could use it. But we also provide this via as an on-premise solution. Come to our booth, talk with us. This is not an easy task to do that within your on-premise architecture. Normally we come to you, we bring you all the Terraform stuff, the HELM stuff, and we help you to set up that cluster in your infrastructure. And you will get a specific invented UI that will enables you to handle the cluster in the same way like in our cloud frontend you see minutes before. I hope that answers the question a little bit. So there is an on-premise solution and there is also a SaaS solution. How to inspect my saved data? As you saw, you could always access the data via Postman, for example. That's the way it works. And yeah, there is no SQL or stuff like that anymore within the technology. So yeah, we cluster REST interfaces, and so you have to use your Postman or something like that. Okay, I hope that answers your question. If you have some further questions, feel free to ask now or to meet me at the booth. And at this time, I say thank you for joining my talk. See you at the conference. Enjoy the conference. Take care. Bye.